Welcome to the Deep Dive. Today we're doing something a bit different. We're stepping into a unique role, almost like your personal guides, maybe even advocates.
That's right. Our mission today is, well, to introduce you to someone truly remarkable, Mr. Peng Yanming.
Exactly. We're going to dive deep into his capabilities, drawing straight from his academic work, his projects, his professional life.
And if your company is searching for top talent, specifically in hardware integration, firmware development,
Then you'll want to stick around.
yeah.
We think you'll see why Mr. Peng isn't just, a good candidate, but potentially a really impactful hire.
And to make that case, we've really dug into the source material. We're talking his resume, of course, but also these detailed reports from two major space-related projects he worked on.
Space projects. Okay, intriguing.
Yeah, one was a high-altitude balloon mission, the other a satellite simulation. Plus, his master's thesis, which focused on control circuit design.
Got it. So lots to cover.
Definitely. Our goal here is to pull out the key insights, the things that really highlight why he's such a perfect fit for those tough technical roles you need to fill.
Okay, so to really understand Mr. Peng's depth, we should probably start at the beginning, right? His foundation at National Cheng Kung University.
Makes sense. The Institute of Space Systems Engineering.
And what strikes me immediately looking at this is that his learning wasn't just like hitting the books. It was very hands-on, building real working systems from the get-go, wasn't it?
Absolutely. That's a crucial point. His education seems deeply practical, which, as you know, is gold for hardware and firmware roles. You see it right away in his project work, theory put directly into practice.
So let's jump into one of those, this first big one from his master's first year. The GEOZONE High-Altitude Balloon Mission, Geographic Environmental Observation Zone.
Right. GEOZONE.
And this wasn't some small-scale lab test, was it? I mean, that sounds ambitious. A balloon designed to collect environmental data. Ozone, temperature, pressure, GPS.
All the way from sea level up to 37 kilometers, that's high.
37 kilometers.
Yeah.
While taking pictures and with the goal of actually getting the payload back safely. That's serious real-world complexity. You've got weather, physics, electronics.
Huge environmental challenges, exactly. And his contributions were very direct, very hands-on. It really showcases his hardware and firmware skills early on.
Okay, so what specifically did he do on the hardware side?
Well, he was responsible for defining what each component needed to do, and then integrating this whole array of sensors and modules. For the balloon itself, think temperature sensors, pressure sensors, even 3 different types of ozone sensors.
3 types, okay, thorough.
Yeah, plus GPS, the main microcontroller Omega 2560, and a LoRa wireless module for long-range communication. E220 400T3OD specifically.
And that's just the balloon. What about the ground station?
For the ground side, he worked with an ESP32S microcontroller, another LoRa module, a precise time module DS3231, and an SD card adapter for logging all that data.
Wow, that's quite a list.
Mm.
It really shows he can handle diverse hardware, selecting it, making it work together.
Right. He wasn't just picking parts off a shelf. He was architecting how they all connected and communicated.
And the firmware. How deep did he get into the actual code and circuit logic?
Very deep. His name is right there on the electronic circuit design sections. And he authored the component and mainboard communication protocol and the crucial pinout table sections.
For both systems, balloon and ground.
For both, yes. That shows real understanding of hardware interfacing, that low-level communication logic. He also contributed to the mainboard program link and the program flowchart for both systems, too. So clear firmware development skills there. He grasped the whole picture, from the physical pins to the software commands.
Okay, so designing is one thing. Making sure it actually survives going up to 37 kilometers, that's another beast. What about testing? Was he involved there?
Oh, definitely. The testing phase was critical, and he was right in the thick of it. Participating in sensor functionality tests for things like the barometer, humidity sensors, those ozone sensors. They even used an ozone generator to properly validate those. And crucially, he was involved in the low-temperature test. They simulated high-altitude conditions, getting components to operate successfully all the way down to minus 35 degrees Celsius.
Minus 35. Okay, that proves the payload box insulation worked and the parts themselves could take the cold. That's serious validation.
It absolutely is. It shows the design wasn't just theoretical, it was robust enough for the actual environment.
That kind of testing takes dedication. And what about the physical construction? Putting it all together.
His work on the arrangement design stands out there too. Components weren't just slapped together, they were carefully soldered onto perf boards, connected with proper HX 2.5 connectors to make sure everything stayed put during flight. Vibration, G-forces, all that.
Right. Practical fabrication skills. You need that robustness.
Exactly. And his role didn't stop at the build. He was key in data post-processing afterwards, taking that raw sensor data, converting it into meaningful physical quantities, even interpolating sparse GPS data to reconstruct the flight path.
So data analysis too.
Yes, and data analysis proper. He actually identified challenges during the mission, like some GPS reception issues at peak altitude, and noted the ozone sensor's slow response time. That shows a really sharp analytical mind, troubleshooting not just the hardware, but the data it produced.
Okay, so full spectrum. Design, build, test, analyze, troubleshoot.
Yeah,
That's impressive for a first-year master's project.
dude, it really is.
And then he took on another big project in his second semester, the Loom 1 ComSat simulation.
He did. LCSPWT Loom 1 ComSat simulating practical work in Taiwan. This was simulating a European CubeSat, LUME-1, but applying it to a really critical problem: forest fire detection.
Forest fires, okay. So how did this simulation work?
The core concept was pretty clever. You have ground transponders. Think of them as remote fire detectors. They detect a fire, send data via LoRa,
LoRa again, okay.
yep, to a simulated satellite, which they called the transceiver. That transceiver then relays the info down to a ground receiving station. It's all about that end-to-end communication chain, simulating a practical, real-world satellite application.
Right, simulating practical work. That sounds like a step up in complexity, managing multiple moving parts, communicating wirelessly.
It definitely was. And you see Mr. Peng taking on an even bigger role here, demonstrating growing mastery. He was the lead author for the entire electronic circuit design, flight software design section.
The entire section, for all three parts.
For all three. The transceiver, the transponder, and the receiver. He essentially owned the electronic and software design for the whole distributed system. That's a significant jump in responsibility.
Huge leap. And I assume the component list got even more complex across those three units.
It certainly did. The transceiver needed environmental sensors, GPS, a main controller, another Mega 2560 LoRa, but also solar charging modules. Power management becomes key for a satellite.
Ah, right. Solar power.
Then the transponder used a smaller nano controller, LoRa, and a temperature humidity sensor. And the receiver, again a nano, LoRa, a time module, SD storage, managing those bills and materials, integrating all those functions across interconnected units.
Yeah.
That's complex stuff. He had to ensure data flowed seamlessly.
Sounds like a delicate dance of data packets flying around. How did he manage the communication protocols?
His work there is really impressive too. Continued focus on the component and mainboard communication protocol and the communication packet concept. He detailed using unsigned integers, scaling factors for decimals, designed specific packet structures like 5-unit and 25-unit arrays.
Okay, getting technical.
Yeah, and importantly, he implemented 2 distinct LoRa channels. One frequency for the ground to satellite link, another for satellite to ground. Plus, he managed the deep sleep and transmission modes of the modules to save power. That shows a really nuanced grasp of wireless comms at a low level.
Power saving again. And it wasn't just electronics, right? There was a physical structure, the CubeSat itself.
Absolutely. He co-authored the transceiver structure design. They built a 2-unit CubeSat model using PMMA acrylic sheets, clever dovetail joints for assembly. He planned the layout of the internal components, the EPS electrical power system.
Yeah, to use the power, right.
Right. The CNDH command and data handling, the brain,
Processing.
and the TT&C telemetry, tracking, and command for talking to the ground. So he understood how the physical shape and the electronics fit together.
And the power system. You mentioned solar panels.
Yes, and this is key. He designed the Solar Panel Charge Control Module, or SPCM. It managed 5 solar panels and, crucially, prevented something called the bucket effect.
Bucket effect.
Yeah, it's where one underperforming panel can drag down the whole array's efficiency. His SPCM design could selectively enable charging channels based on voltage to avoid that. That's a sophisticated, real-world power management solution for a satellite system.
Wow. Okay, so he wasn't just plugging things in. He was designing custom solutions for complex problems like power optimization
Yeah.
and validation. Did he see this through to the end?
He did. He led the system operation results and the data post-processing and data analysis, ensured the whole chain worked, from sensors capturing data to the ground station storing and analyzing it. converting raw values, plotting battery voltage, temperature, pressure, UV, GPS coordinates over time.
The full stack.
Exactly, a full stack approach, ensuring the system delivered reliable, meaningful data from start to finish.
Okay, these projects are incredibly impressive, really showing hands-on capability. Now, let's pivot to his master's thesis. This sounds like where he took all that practical skill and focused it on a really fundamental engineering problem.
That's a great way to put it. The thesis title is Design and Application of Control Circuit on Solenoid Valve.
Solenoid valves. Okay, they're everywhere, right? Factories, fluid system.
Everywhere. And the core problem he tackled is something many industries just live with. Solenoid valves are power hogs. They need a strong kick of power to open initially, but much less to just stay open.
So lots of wasted energy and heat.
Exactly, a common issue. His goal was elegantly simple. Design a control circuit to dynamically adjust the voltage high power to open, lower power to hold, optimizing power consumption without sacrificing performance, like the flow rate.
And he framed it as a from-scratch-to-finish hardware development process.
Yes, explicitly, to demonstrate that entire engineering journey, which is exactly what a hiring manager wants to see proof of.
And he didn't just land on the final design immediately, did he? There was an iterative process.
Very much so. That's crucial in good hardware design. He went through 3 generations. The first generation was basically a baseline, just replicating a simple relay, switching the valve between full 28 volts and 0.
Okay, standard way.
Right. Measured average power, 16.38 watts. This step validated his basic transistor switching and the isolation circuit design. Foundational stuff.
Got it. Then generation 2?
Second generation. He introduced a dual voltage approach, switching between 28 volts to excite the coil and 18 volts to hold it open. Power dropped nicely, down to 10.14 watts.
Better, but not the end goal.
Not quite. And critically, he observed something: significant current ripple. And he diagnosed it, attributing it to the 150 kilohertz switching frequency of the specific off-the-shelf buck converter module he was using.
So he didn't just accept the off-the-shelf limitation. He identified it as a problem to solve.
Precisely. That insight, that critical eye, drove the refinement into the 3rd generation. That's real engineering.
Okay, so the 3rd generation, this is the big innovation.
This is the culmination, yes.
Yeah.
3rd generation control circuit. It delivers what he termed a stair-shaped voltage output.
Stair-shaped?
Yeah, think of it visually. Starts high, 26.7 volts for that initial kick to open the valve. Then it drops to an adjustable lower holding voltage. He could tune this anywhere from 0 volts up to 25.7 volts. And then, of course, 0 volts for off.
Adjustable holding voltage, okay. And the results?
With optimized parameters specifically, a super short coil exciting duration of just 0.035 seconds and a holding voltage dialed down to 8.8 volts, he slashed the power consumption. Remember the baseline, 16.38 watts.
Yeah.
He got it down to just 3.23 watts.
Whoa, wait, from over 16 watts down to just over 3.
That's an 80% reduction in power, 80%, while maintaining the same flow rate through the valve.
Pause. Okay, let that sink in. An 80% power saving on a common component. For anyone listening, maybe not deep in circuit design, what does that mean practically for a company?
It's huge. Think about battery-powered devices. Suddenly they last much, much longer. Think about systems packed tightly with electronics where getting rid of heat is a nightmare. Less power means less heat.
Right. Smaller fans, maybe no fans.
Exactly. It could mean smaller product designs overall, lower operating costs for industrial systems, longer maintenance cycles. It potentially opens doors for applications where power budgets were just too tight before. It hits the bottom line: efficiency, reliability, even enabling new features. It's a direct competitive advantage.
And it wasn't just a fixed solution, right? You said adjustable.
Key point: he built in customization. Variable resistors allow for fine-tuning, that stepless micro-adjustment of both how long that initial high-voltage kick lasts, the coil exciting duration, and the level of the lower holding voltage.
So you could adapt it.
Precisely. Tune it for different solenoid valve models, different required flow rates, even different operating pressures. He tested it successfully from 5 bar all the way up to 45 bar using the same optimized settings. That proves its versatility.
That's incredibly flexible design.
Yeah.
Can we peek under the hood? Any specific circuit techniques that stand out?
Sure. For the power circuit, he used efficient switching buck converters, specifically the LM2576, which has a more stable 52 kilohertz frequency compared to the one causing ripple earlier, to generate both a fixed control voltage and that adjustable holding voltage, all from a single 28V input. about design.
Okay.
Isolation was critical. He used optocouplers, LP250s, to keep the low power control signal totally separate from the high power valve load, protects the sensitive stuff from surges.
Essential for reliability.
Absolutely. Then his transistor switching circuit, combining NMOS and PMOS transistors, was really well done for precise power control and for creating that timed high voltage pulse. He cleverly used basic RC resistor capacitor circuits, but with adjustable resistors. That's how he got the variable coil exciting duration for the stair shape.
Ingenious use of simple components.
Very much so. And finally, protection. He included essential flyback diodes to handle the inductive voltage spike you get when you suddenly cut power to a coil like a solenoid. Protects the whole circuit from frying itself.
Okay, so putting it all together, this thesis wasn't just academic theory. Mr. Peng identified a real problem, built a solution from scratch, rigorously tested it, iterated on the design based on observed limitations, and delivered truly remarkable, practical improvements.
That's it, exactly. That iterative from scratch to finish process, tackling a fundamental efficiency problem head-on. That's immensely valuable to any hardware team. He didn't just understand it, he did it.
And this deep technical skill from his projects and thesis, it's complemented by professional experience too, right?
Yes, and this adds another really important dimension. Before his master's, he worked as a quality engineer at ADC Aerospace Industrial Development Corporation from 2019 to 2022.
Aerospace quality control. Okay, that sounds rigorous.
Extremely. His role involved maintenance quality control and providing solutions for production line problems. This speaks volumes about his meticulous attention to detail, his process-oriented thinking. He even got a Lockheed Martin Engineering Capability Certification and an internal company award for quality improvement.
That's quite diverse aerospace QA, then deep circuit design, complex space systems simulation. How does that QA background give him an edge as a hardware developer?
It's a massive advantage. Someone with that background understands reliability from the ground up. They know how things fail in the real world, how to design against failure, how to implement processes that ensure quality and consistency during manufacturing. It's not just about making a circuit work once on the bench, it's about making it work reliably every time for the product's lifetime. That perspective is gold.
Builds confidence in the designs he produces. And he's also an inventor. Patents.
2 Republic of China patents, yes. One for a synchronous all-flip hinge device, another for an axilless hinge. This isn't just executing designs, it shows genuine innovative thinking, the ability to devise novel, practical, patentable solutions.
Creative problem solving. And he's kept his skills current, too. I see an Arduino certification from 2024.
Yep, formal recognition of his embedded systems and microcontroller skills. Staying sharp.
And it's not just electronics, is it? He seems versatile.
Very. Proficient in Python, which is huge for data analysis, scripting, automation. And he uses CAD software like AutoCAD and SolidWorks for mechanical design and integration. That ability to bridge electronics and mechanical design is incredibly valuable.
Allows him to see the bigger picture.
Exactly. And across all these projects, the reports consistently mention his team contributions. He's clearly collaborative, not just a solo genius. He works well with others, bridging disciplines.
Okay, let's try to synthesize this. For you, the listener, considering Mr. Peng, you're seeing this blend. Rigorous academic knowledge, yes, but heavily backed by extensive hands-on experience.
Experience in really complex hardware integration, firmware development, demonstrated through those space projects.
Then there's that proven track record in power optimization, designing circuits from scratch, shown so clearly in his thesis.
Plus, a professional background steeped in aerospace-level quality assurance, that focus on reliability and process.
This isn't just someone who knows about hardware. This is someone who builds, tests, refines, optimizes, ensures quality, and even invents.
And that's precisely why he stands out as an exceptional candidate for hardware integration and firmware development roles. His proven ability to design, build, test, troubleshoot complex systems, combined with that sharp eye for quality, for efficiency, for problem solving. He's the kind of person who doesn't just fill a role, but genuinely makes an impact. He thinks from scratch to finish and delivers tangible results, like that 80% power saving.
So let's leave you with this provocative thought. Imagine the real, tangible impact of bringing someone with Mr. Peng's proven from-scratch-to-finish approach into your team. Someone who has demonstrated the ability to dramatically improve something as fundamental as power consumption. What new levels of innovation, efficiency, and product reliability could he unlock for your company?